Hi, everyone. I'm going to share some of what we call fundamental concepts, which are basically the scientific and some of the terminology principles that we think you need to understand before you either facilitate the game or for your participants, they should at least understand the terms before they play the game. If you're teaching kids, this becomes especially important. It might be less important for local leaders if that's who you're working with. But we have this available for you to use however you want. We'll have the slides available. You could take some of them and use them, alter them how you want. So let's get going. As soon as I figure out how. There we go. All right, so this is some of the stuff that we'll be covering. Two basic topics. One is water quality. The second one is resilience. Under water quality, we definitely need the kids especially to understand what is a watershed, what are non-point source pollutants, how do humans alter the land, what are some types of non-point source pollution, and what about the ones that we're looking at specifically in the game? We'll talk a little bit about natural levels of sediment and nutrients, some of the sources and impacts of excess sediment and nutrients. And then we'll talk about pollutant loads, the clean water goal, and pollution units, which is the way we track numbers for pollution in the game. Then we'll switch to resilience and kind of the same sequence. We'll talk about the definition of coastal resilience, how flooding is a natural process, the impacts of severe flooding, and then looking at resilience to flooding. We patterned the game after the community rating system. We'll talk about that and the way that we use resilience units in the game. So let's get going. So a watershed is the area of land that drains to one particular lake, wetland, stream, or river. And depending on where you're looking at the water quality, your watershed might be a different size because, of course, they come in different sizes that are nested together. So, for example, if you were looking at this point on the land where the stream comes out of this basin, you'd be looking at a much smaller watershed within the larger watershed. And we care about that because this is all the water that is coming to one area. And if we're trying to figure out if the water is staying relatively healthy, we have to have some place where we are gathering to measure and check it. So let's take a look at this landscape. You can see it's a little slice out of the earth, and it's a fairly undeveloped landscape. There's forests up at the top. We've got some sort of grassy areas. This is a forested wetland. And over here is a bog. We've got a lake, and you can see the only development that shows up on here are these little tiny cabins. And there's not even really a road into them, so they must have some way they hike in. And then you can see the underground area where groundwater would flow through. So it's raining. And what's going to happen? If you watch, there's some animations in here that kind of help tell the story. So as it rains, it's going to first hit this upper area where it's falling. It'll get soaked up by the trees, and it'll soak into the ground. Over time, as the rain progresses, the water that soaks into the ground ends up in the groundwater. If soil acts as kind of a natural filter and helps filter out some of the potential contaminants that might be in there, it also cools the water. So by the time the groundwater enters some nearby waterway, it should be cooler and probably a little bit less full of nutrients, minerals, whatever else was in there than it was, because a lot of that gets captured by the soil. Now, if it keeps on raining and it turns out to be a really intensive rainstorm, you might see some other things happening. As that rain totally saturates that upper level, it will start flowing downhill. It will not necessarily flow really quickly because we've still got these processes at play that are helping to soak that water up and slow it down. For example, the water that reaches this forested wetland or the bog down in the lower upper right will be basically held by that wetland. It acts like a sponge and holds that water there so that it gets released very slowly over time. And you can see that we've got water that has flowed into the lake, just a little bit of it got water that's flowed in through groundwater. So that's pretty much what a natural system would do. And if we look at the numbers, and people have done this in a fairly undeveloped landscape, you'd see maybe 50% of that rainwater ending up back in the groundwater, and maybe 10% of it flowing directly across the land, overland flow, and probably about 40% either getting absorbed by the plants or ending up back out in the atmosphere some way or another. So, all right, now, so we think of that as being slow and steady. In a natural landscape, you'll usually see slow and steady movement of water across the land. It lasts longer, it takes better care of the plants, and there's just so many good things about the way it works under a natural system. Now, let's, this is our watershed here, this outer boundary. It's got this is our watershed games. So we have the small stream version, we have a lake, the large river, which in our brand new game is flowing into coastal waters. So, and this could be Great Lakes coastal waters, even though they're freshwater, or it could be one of our coasts of the US where they're oceanic. So this watershed, if you look at all this area along all the waterways, it's pretty developed. And when something is developed, it means we've got a lot of other stuff going on in the land. And that's what we're going to talk about next. So here's our same watershed that we started out with. Now it's been developed. So you can see there's a big urban area up at the top. There's a farm with animals, lots of pasture land, probably some agriculture that we can't quite see here. You can see there's some parking lots. This is a big parking lot that has replaced the forested wetland that used to be there. Let's see, we still have a little cabins. This area is still pretty decent. So it's raining. Now, when rainwater falls on all the human disturbed areas, which could be industry too, there's none showing on this one, it is falling on a lot of hard surfaces, or what we call impervious surfaces, that don't let water soak back into the ground like it would naturally. And in those cases, we see the water flushes off the land pretty darn quickly because there's no way for it to absorb in. It also means there's less vegetation to soak it up and send it out to the atmosphere or into growth. So what we're looking at here is same type of rainfall, but when I start animating this, you'll see a really big difference. You see the water is flowing really quickly across the land. And if you were watching closely, you would have also seen that a lot of sediment has come off of these fields. And even those fields and, pasture land could act like impervious surface because it's very compacted. So it doesn't always have to be pavement or rooftops. It can be things like compacted soil. Of course, our parking lot didn't do anything to help hold the water. And if you look down at our lake, you'll see that our cabins are flooded. So, and it all happened really quickly. You also notice that there's very little groundwater coming back into the lake. So the water that's on the surface of the land is getting warmed by the sun as it flushes off. And that means we have warmer water in the lake because very little of it's getting cooled in the ground. So there's kind of three things going on here. There's a lot more water flowing faster and with more force across the land, which can scour out streams. It can flush all kinds of stuff off the land. It could be flushing pollutants off the parking lots, all kinds of different things like that. And it's taking exposed soil with it, which means we're getting not just soil, we're also getting fertilizer, pollutants, and other unwelcome materials that are heading into our lakes, wetlands, streams, and coastal waters. So all that water that moves so quickly is also causing flooding because it's happening so fast and there's just nowhere for the water to go quickly. And when scientists look at that, they see that in a more, and I also forgot to mention that we also seem to have a giant algal bloom here in the lake because there's so much more nutrients coming in than there would have been prior to this. So let's look at what scientists find. So remember before there was about 50% of the water would go into the ground. Under a really developed watershed scenario, only about 10% soaks in. And basically those numbers are flipped. You got about 50% of it coming down the landscape quickly after a big storm. And again, there's about 40% going up into the atmosphere, but or going into vegetation, but a whole lot less is getting into vegetation. A lot more is just ending up back out in the atmosphere. All right. So that's kind of what we worry about with development, and that's why we think it's important to be teaching these things. Fast and furious is how I like to think of this. And if you start thinking about what that means in terms of non-point source pollution, non-point source pollution is defined as rainfall or snowmelt moving over and through the ground that picks up and carries pollutants, finally depositing them into waterways. And, you know, we're talking in the watershed game about sediment and nutrients, nitrogen and phosphorus, but there's other things going on, like I intimated in that last slide. So anything that gets put on the roads will get flushed off into the water, unless it's captured by vegetation right near the roads, including things like road salt, oil, gasoline, heavy metals, all kinds of stuff. And again, you can see the evidence in these pictures. We also didn't talk about bacteria, which definitely is a big issue. Sediment has a lot of issues we'll talk more about in a minute. So when we talk about non-point source, it's not just the things we cover in this game. We've just picked the ones we thought were most relevant to the game and to the people we're working with. So it's really important at this point to say, wait a minute, we got to say something here. Sediment, phosphorus, and nitrogen are essential and natural parts of a healthy environment. And we really want to hammer that point home. They are not pollutants in and of themselves. They are only pollutants when way too much enters our lakes, streams, wetlands, and coastal waters. And in fact, lakes and all these places come in different levels of, you know, they've got different natural levels of nutrients. So what we're talking about is, given what was natural for a system, whether it be a really productive lake in, you know, a kind of plains area, prairie area where there's a lot of nutrients that reach it, or whether it's a really, really unproductive lake in northern Minnesota or somewhere, they each have a natural state. And we only talk about these things as pollutants when they're in excess of what the system is used to coping with or using. And so when we talk about background levels, we have to remember that some erosion is not only natural, it's also very important. The deltas and riverbanks that we see, like the Mississippi River, for example, as you can see in this picture, depend on sediments. In fact, some of the most nutrient-rich and fertile agricultural areas are where there's a lot of sediment getting deposited. It's very natural. Sediment-rich areas often have really high biodiversity because they're so rich. Nutrients, well, we wouldn't be here. You know, they're essential for all life. They're continuously cycling through plants, animals, and the environment to support life. And, you know, DNA relies on nitrogen and phosphorus. So there you go, really important. And you don't want to let that slip when you're facilitating the game with people. However, we have a whole lot of ways that we add excess to our systems. You know, these are just some examples here. Erosion, atmospheric dust is actually pretty big. Nitrogen, you may not realize, maybe you haven't heard that cars generate a lot of atmospheric nitrogen, which then ends up deposited. Human animal waste, urban runoff, same in phosphorus, but we also have a lot of phosphorus that's in decaying plants and organic waste from industry and other places. This is not an exhaustive list, and I'm not going heavily into it. We just want to help you be thinking about where these things come from. That's part of what the game does too. I also want to teach you just a few things about how phosphorus, nitrogen, and sediment behave in the environment. And part of the reason that we have done this is that we are including phosphorus and nitrogen as separate nutrients in the game. We had thought about lumping the two, and we realized that in some areas of the country, phosphorus is more critical in terms of causing algal blooms and things like that. In other areas, it's nitrogen. So we think based on what the conditions are like in your area, you may want to choose one or the other and play for that to make your points more strongly. So let's go through this slide real quickly. Key things to remember. Phosphorus is sticky. So just by virtue of its chemical structure, it will stick to sediment particles. So whenever you're talking about it or working with people, it's good to keep that in mind. That, you know, wherever the sediment is moving, it's taking quite a bit of phosphorus with it, probably, as long as there was a source that got phosphorus associated with that sediment. And it is the key nutrient that we have to control to reduce or control algae in much of our inland waters, and in some coastal cases as well. Nitrogen is different. It's soluble in water. And I kind of like my image here of, you know, little nitrate molecules floating downstream. They would actually be soluble in the water, but I couldn't think of how to show you that. And they will go, nitrate goes wherever the water goes. So that's one of the big ways that nitrate moves around in our environmental systems. So that also includes groundwater, which is why we are often concerned about nitrate in well water, because nitrate goes right down into the ground, and, you know, it ends up back in waters of the US, but it can also cause some issues. So it's the key nutrient that we have to reduce to control algae in many coastal waters. Important things to know. So a little bit more about the numbers. When we talk about lakes, for example, we talk about how productive they are, in the sense that the more nutrients coming in, the more they can grow in terms of plant matter, which then supports more aquatic insects, invertebrates, and fish. And also how green and scummy the lakes are. So a eutrophic lake is one that's very high productive and has the potential to have a lot of green, scummy algal blooms. For phosphorus, the amount that causes a lake to be considered or classified as eutrophic is about 200 parts per billion. So that's not much. I mean, down the corner, I have, you know, one sheet in a roll of toilet paper that goes from New York to London. It's not much. For nitrogen, it's about 500 parts per billion. The other thing that I like to make sure people think about is that when you add fertilizer, I don't care if you're a farmer, if you add it to your lawn, if it's a golf course, if you spill a little fertilizer on your driveway, you probably think, well, just a little bit, it's probably fine. But you have to remember that the concentrations we use on land are far, far higher than the ones that influence how healthy our lakes are. So, or streams or rivers. We talk about fertilizer, the numbers that are on a fertilizer are referring, we're talking about parts per million. So it's 1,000 times more concentrated than the levels we think about for our water bodies. So it doesn't take much spillage to cause problems. And I think it's an important thing to make the point of. You should know how much, you know, nutrients your soil needs and not overload it, because it will end up where you don't want it. A couple of things is just 1 pound of phosphorus, I've seen this in very reputable sources, can yield somewhere around 500 pounds of algae. That's pretty dramatic. And another important thing is that at elevated levels, greater than 10,000 parts per billion, nitrates in water can cause severe illness in infants and domestic animals. So that's why we test well water for nitrates. So based on where you live, whatever your region is, what kind of soils you have, what human impacts are going on, what type of water body it is, either nitrogen or phosphorus might be the trigger that causes excess algal or plant growth and other impacts we'll talk about in a second. So you should do your homework if you're facilitating the game and figure out what works best for you. So impacts of excess nutrients. This is so short of a list because there's so much more, but at least gives you a feel for it. Certainly too much aquatic plant or algal growth. And it's usually kind of one or the other, because one of the things that can happen with too many nutrients or sediment coming in is you can lose water clarity. And that can mean that the algae do better than the aquatic plants, which need a lot of light to penetrate to support them. Aquatic plants are really important for habitat for aquatic insects and larval fish. So losing them can be significantly important in habitat and aquatic life. Algae can be toxic. You all know about toxic algal blooms by this point, I'm sure, harmful algal blooms. And it can result in water that is not swimmable, drinkable, or fishable, which is what we're trying to attain. All right, so now let's switch to sediment. And When you think about sediment getting into water, this is from the St. Louis River and coming into Lake Superior. It's a tributary that just is on clay banks and it erodes like crazy. All that sediment absorbs more heat from the sun and thus can really increase water temperature significantly. It also, as you can tell, reduces water clarity and light penetration. We already sort of mentioned that in the last slide. It also, as we talked about, phosphorus sticks to sediment. It brings phosphorus with it as well as some nitrogen, increasing potential for severe algal blooms. And it reduces habitat near shore. We talked about that a little bit too. The other thing about sediment, when you're thinking about fish and aquatic critter habitat, is that a lot of fish need nice, clear gravel beds to spawn for egg incubation. They also use some of these areas basically as shelter and ways to get into the right temperature water and things like that. So sediment on the bottom can create this embedded situation where there's just no more good spawning habitat. It also very much, this is a terrible picture, I realize, affects the aquatic insects who also really need clear water in many cases, or non-sediment laden water. And when we talk about it, it's kind of interesting to see, this is from kind of upper Midwest, but fish that are adapted to clearer situations are very much affected by how much sediment is in the water. And in this case, the unit that was used to measure them is turbidity. You can also measure for total suspended solids, but in this case it was turbidity. And so the scale doesn't really matter too much. It's a way to basically show you how much. So you can see how this is a very clear sample. Over here at 400 NTUs, it's a very cloudy sample. So, and we've got these gradations in between 2, 10, 40, and 80. So what happens? What do the numbers mean? Let's see if I can, okay, even at 10 NTUs, you don't really want to know what that stands for. Well, it stands for nephelometric turbidity unit, so just let it go. But fish start acting stressed, particularly fish adapted to clear situations. When the number increases, when you see numbers up around 80, which to me also doesn't look incredibly cloudy, I'd probably swim there, fish start abandoning cover. They swim away from the turbid water. They increase their respiration rates, a little bit harder to breathe, I guess. They feed less and they start coughing. And who knew? I didn't know fish coughed until I started looking into this stuff. And when you get to about 400 NTUs, fish start growing more slowly. Eggs hatch more slowly. These things can slow down growth, but if they don't last too long, the fish will survive and they'll be okay. But there's also this thing about time. So as the time gets longer, if these high turbidity levels stick around, you get to a couple of months or a month or two and you'll see death. And so again, it all has to do with what the fish are adapted to begin with, because certainly there's waters that are naturally fairly turbid and there are fish that still live in those. So it's a matter of what your baseline situation was and how much things have changed. And that's where the science comes in. All right, we're finishing up the water quality unit. And the last thing I want to say here is that a lot of times we think about things like nutrients or chemicals in terms of their concentration in water, or in other words, how strong is it? And that would be like, I'm making a cup of tea and I want to see how I want to put sugar in it, and I put in a teaspoon or two, and we're looking at how many teaspoons per cup of tea, right? In the natural environment, when we're measuring things like phosphorus, we might say, if you get a water sample and look at it, like these water samples here, you'd say, well, how many micrograms are there, or parts per billion per liter of micrograms of phosphorus per liter of water. But when we're talking about watersheds and how do we manage health of the water in the watershed, we don't really talk so much about concentrations. We talk about loads. So we talk about total pollutant load, and that's what this game, the Watershed Game, is based on. So just for your own knowledge and understanding, it's not, when we're talking about loads, we're talking about how much is coming in to a particular unit of water over time. So we're looking at, it would be like you're trying to lose weight. And so it would be, well, on average last week, I consumed so many calories per day. If you consume too many calories, you will be off track. You will gain weight, which is not what you want to be doing. So by looking at load, it gives you a way to estimate what you need to do to fix the situation over time. And it has to do with how much water is coming through and all kinds of things. So we might say average calories consumed per person per day. We've added this time component. And in the case of a natural environment, it'd be more like average tons of sediment transported per day, per week, per month, per year to a lake or stream. And that's what we're looking for. So in the game, participants will be working to meet a clean water goal by reducing pollutants to a level that will protect human health and protect and restore aquatic ecosystems and their watersheds. And it will be based on a load. It's actually based on our real Federal Clean Water Act's Total Maximum Daily Load program, which is a stupid name for a program, but what it really is saying is that we require the load of non-point source pollutants, sediment, nitrogen, or phosphorus, to remain below a level that has been determined to be protective of that portion of the watershed, that water body, protective for human health and the environment. So that's what the game is looking at. And it's based on scientific study, monitoring, lots of people out there monitoring, and modeling. So we put all this stuff together into a package and say, yep, we've figured it out for this watershed. You got to keep phosphorus below such and such. And, you know, that's what the Clean Water Act is about. It's about fishable and swimmable for all. Okay, so let's move on to the second part, and that's coastal resilience. And resilience is talking about helping a community or a watershed build the ability to bounce back quickly after hazardous events. And that could be hurricanes, it could be flooding, it could be coastal storms, it could be tornadoes in certain parts of the country. And in the case of the watershed game, we decided to look at flooding. So the idea is helping communities to be proactive rather than reactive, fixing all the damaged structures, trying to reduce the pollutant load that came in with the flood. Why? Well, informed, prepared communities will rebound more quickly from weather and climate-related events. The environment will stay healthier, a lot less damage, loss of life. So by being resilient, by being proactive, you can reduce the negative health, environmental, and economic impacts. And we all are pretty aware by now that climate change has severely influenced the timing and severity of rainfall and snowmelt events. And this little graphic here is showing rainfall increases by percent in the heaviest events in various areas of the country. And barring the Pacific Northwest, all areas of the country are having more severe events. And in fact, if you look at flooding, in the Mississippi River Valley, the Midwest, and the Northeast, there's definitely more flooding going on. And US coastal flooding, this is now, has actually doubled over a matter of decades. So that's why we chose flooding. It's really, really pertinent right now in coastal areas. And again, I have to stop you and say, wait a minute, flooding's not all bad. Flooding is natural. Flooding is important. Some of the benefits that we see from flooding are recharging the groundwater, like we were talking about before, increasing fish production by providing more nutrients in places that need them, creating wildlife habitat, so this is in a more natural situation, recharging those wetlands so that they function really well as sponges, constructing floodplains, helping us have areas that water can sit and soak in, and rejuvenating soil fertility. But again, severe floods have severe impacts. So not only loss of property, potentially human life, but on the natural side, accelerated erosion, more nutrient runoff from developed areas and mobilization of nutrients, moving them through the system, disrupted drainage systems, spills of sewage, animal waste, discharges of toxic substances from industrial, agricultural, and urban areas. So there you go, proactive pays off. And in the game, we're modeling what we're doing, just like we did with the Clean Water Act, after the Federal Emergency Management Agency, FEMA's National Flood Insurance Program. So we used what they have is a community rating system, CRS, which is incentive based. So it's not forcing communities to do things, it's giving them good incentives. And they do that by giving them credit points for actions they take that increase their community's resilience. So they have to have flood insurance. So those credit points can be used to reduce their premiums for flood insurance. If you look over at the chart on the right, you'll see that it's a point structure. And like say a community that has earned 1,500 to 2,000 credit points, based on where they are in terms of how close they are to the water body, where they are in the floodplain, they might save between 5 and 15% of the premium they would have had to pay for their flood insurance. So it's a system that helps encourage proactive work in your community. So that's what the game is modeled after. I think I forgot to say that when we're talking about pollution units, rather than do something like NTUs or something for sediment and then PPBs for phosphorus and nitrogen, we just originally used points, but we've now changed our language in our more recent games to pollution units or PUs. And for the Watershed game, when we play, only the coastal version does resilience, but when we play for that, we're talking about resilience units, RUs. So now you're familiar with PUs and RUs. Anyway, so that's kind of in a nutshell what I wanted to cover. I hope it's clear enough, and we can certainly talk about it when we're together. And I'll be modifying and adding some more descriptive notes to the notes section of the PowerPoint so that it'll be easy for you to take this and adapt it for your own use. So let's just end by going back to our little picture of the watershed. And by the time you've left here, you'll have been exposed to all these different games and hopefully you'll really enjoy it. So thanks everybody. And I'm stopping sharing and stopping recording at this point as soon as I figure out where all my little buttons are. So hold tight for a second.